or what is the functionality of this status flag register? Anyone?
It's tell us the status of the operation.
These are some register, right? And what is the size of status flag register? These flag registers are 32-bit registers.
Yes, ma'am. 32-bit.
Yeah,
yes,
but another thing is we can represent these 6 status flag registers when and how. There are 6 status flag registers for Pentium 32-bit processor. And the name of these flag registers are zero flag register, carry flag register, auxiliary flag register, overflow flag register, then parity flag register, and sign flag register. So these are 6 status flag register. And what is the functionality of status flag register? It will only represent the status of the microprocessor after any arithmetic, logical, or relational operation, right? So after the operations, these flag registers value will be changed. So some operation can affect all these 6 registers. Suppose after addition operation, we will get 6 different value of these 6 status flag register. Or after increment operation, maybe 3 or 4 flag registers will be affected, right? So some arithmetic operation can affect all the flag registers, or some operation can affect only 3 or 4 flag registers. So in the last class, we discussed about the first 2 status flag register. One is zero flag register and another is carry flag register. So this zero flag register can have 2 types of value, right? After any arithmetic or logical operation, we can change, how we can change the zero flag register? We can set the zero flag register, or we can clear the zero flag register. Set means the value of zero flag register will be 1. And when the zero flag register is cleared, that means its value will be 0, right? So when ZF equals to 1, that means the zero flag register is set. When ZF equals to 0, the zero flag register is cleared. Okay. So how we are going to set the zero flag register, clear the zero flag register? Obviously, it depends on the type of operation, as well as it depends on the size of your operand and what type of value you are going to add, subtract, right? So for this operation, move AL 15, this is decimal number, and then add AL 12. So what will be the result, or what will be the value of ZF register after this addition operation? We know that if the result of any arithmetic operation is 0, then the value of ZF register will be 1. Otherwise, the value will be 0, right? So what will be the result of this addition operation?
0.
This Y0, the result of addition operation. AL is 8-bit register, right? So we can
27.
write the binary representation. Yes, the result will be 27. The result is 27, which is not 0. That's why zero flag register will be 0, right? And for this operation, move AL 12 sub AL 12. So for this subtraction operation, the result will be 0. So when the result is 0, the zero flag register will be set. That means ZF equals to 1. So when the result of arithmetic operation is 0, ZF equals to 1. Otherwise, ZF equals to 0, right? So this is zero flag register. What is carry flag register? How its value will be changed? Carry flag register. After the arithmetic operation, we can change the value of carry flag register, but how? The first condition is the arithmetic operation should be done on some unsigned numbers. The number should be positive or unsigned number, right? And the range of values depend on the type of your operand. Suppose your operand is 8-bit register, so the range of unsigned integer will be 0 to 255. Suppose your destination operand is AX, so it's a 16-bit register and its limit or range is 0 to 65,535. So how the carry flag register value will be changed? When the arithmetic operation will be done on some unsigned number, and after that if we get a result which is outside the range, that means if the result is less than the lower bound or greater than the upper bound, then the value of carry flag register will be 1. Otherwise its value will be 0. Or in another sense we can say that if the result has a carry bit or if the result has a borrow bit, then this carry flag register will be set. So can we give an example? What will be the example just give me an example where the value of carry flag register will be 1. Suppose the data is move AL 97, then add AL 180. The instruction is move AL 97 at AL 180. So now if we add these two numbers, the result will be 7, 9 plus 8, that is 17, 277. Now look, the destination operand is 8-bit register and its higher bound value is 255, but the result we got is greater than 255. So for storing 277, we need more than 8-bit, but this register AL has how many bits? 8 bits. That's why after this result, the value of carry flag register will be 1. Is it clear?
Yes, ma'am.
Yes, ma'am.
And for any negative value, the value of carry flag register will be 1. So when the operation will be performed on some unsigned number, and if the result is out of the range, then carry flag register will be set. Otherwise, it will be cleared. Now the third one is overflow flag register, or we can call it OF register. So OF means overflow flag register. Okay, so the previous one, carry flag register, was a flag register where the value will be changed based on the operation on what type of number, on some unsigned number. Now, in this flag register, if the operation will be done on some signed number, then we can change the value of overflow register. Now, all the operation will be done on some signed number. And after that, if the result is greater than the lower bound or higher or maximum, what will be the, let me write the size at first. So for 8-bit register, 16-bit register, what will be the range of value for signed integer? Signed means some numbers are positive and some numbers are negative, right? AL, AH, BL, BH, CL, CH, all these registers are 8-bit register. So what will be the range of positive signed number or negative signed number? What is the range of 8-bit register?
Minus 128 to minus 1.
Minus 128 to
Minus 1.
plus 127. Look, when the register is 8-bit register, and if you're going to store some signed number, some positive or negative number, at that time 2 to the power 8 equals to 256 will be divided into 2 halves. In each half, we'll get how many numbers? Total 128 numbers. So first 128 numbers will be negative, minus 128 to minus 1. There are 128 negative numbers, and from 0 to plus 127. These are positive numbers. So this is the range. Okay. So now after an operation, suppose the operation is an addition operation. So move AL 72H, hexadecimal number, and AL EH. Okay, so what will be the value of overflow flag register after this operation? The first instruction is move AL 72H. So what is the binary representation of 72H? It will be 0, 1, 1, 1, 0, 0, 1, 0, right? And then add 0EH with this number. So the binary representation of 0EH will be 0, 0, 0, 0, 1, 1, 1, 0. Now, if we add these two numbers, what will be the result? 0 plus 0, that is 0. 1 plus 1, 0, we they carry 1. Then 1 plus 1, 0. 1 plus 1, 0. Then again 0, 0, 0, 0, we they carry 1. So if we consider these numbers 72H and 0EH as unsigned number, but before that we have to convert it into decimal, right? The decimal value of 72H is 114, and obviously it's a positive number, and the decimal representation of E is 14, right? Think about some unsigned number. If 72H and 0EH, if 114 and 14, these are unsigned number, if these are positive number, now look at the result. The result has a carry bit. At that time, the value of carry flag register will be 1. But in overflow flag register, we have to consider these given numbers as signed number. Now look at the MSB. The most significant bit is 0, which means that 114 and 14, these are some positive numbers, right? Or in decimal, we got 114 and 14. So the sign is plus. These are two signed numbers, right? These are two positive numbers. So now if we add this two positive number, what will be the result? 4 plus 4 equals to 8. 1 plus 1 equals to 2. 1. Now look at the range. The range of positive number is 0 to 127. That means 128 cannot be stored inside AL register when we are considering some signed decimal number. That's why the value of overflow flag register will be 1. Did you get the difference? The difference is when the numbers were unsigned number, at that time we will change the value of carry flag register. But now we're considering these numbers as signed number, and these two numbers are positive number. What is the range of positive number for 8-bit register? The range is 0 to 127. But the result we got, its equivalent decimal number is 128, which is outside the range. So after an arithmetic operation on some signed number, if the result is out of the range, then the value of overflow register will be 1. Is that clear?
Yes, ma'am.
Yes, ma'am.
And another thing, we are not actually considering the sign bit here. For overflow register, you just have to calculate the decimal number. That if you are adding some two positive numbers, now what is the result? Just convert it into decimal. If the value is outside the range, then overflow register will be set. Okay, so when the numbers will be unsigned number, and after the operation, if we get a carry or borrow bit, then the carry flag register's value will be changed. But if the operation will be done on some signed number, and if we get some carry or borrow, then the value of overflow register will be changed. So signed number is related to overflow flag register, and unsigned number is related to carry flag register. Clear? Is that
Yes,
clear?
ma'am.
Can you solve this problem? Move AX. Now AX is 16-bit register. 0 FFFBH, then sub AX 7 FFDH. Now you have to find out what is the value of or how the overflow flag register will be changed after this operation. So now the destination operands are 16-bit register, and if we want to figure out the value of OF, we have to consider these numbers as signed number. So at first convert the number into binary. So what is the binary representation of FFFB? The binary representation will be 1111, 1111, 1111, and then 1100, right? Now what about 7FFD? 0111, then 1111. The last one will be 1101, right? Now we have to subtract the second number from the first number. Then what will be the result? So after this subtraction, if you get, at first you can convert the result into decimal, right? For this 16-bit register, the range of positive number is, what will be the range of number? Minus 32,767 to minus 1, then 0 to 32,767. This is a range of positive number as well as negative number. So if the result is outside, out of the range, then the value of overflow register will be 1. Is that clear?
Yes, ma'am.
Okay, so this is overflow flag register. Now the next one is sign flag register, and its short form is sign flag. Okay, so now this flag register also depends on the type of operation as well as when the operation will be done on some signed number. What was overflow register? In overflow register, we just perform some operation on some signed number, and if the result is outside the range, then how we change the value of overflow register?
We set the overflow register 1.
Very good, right? So now in sign flag register, suppose the operation will be done on some signed number, and this sign flag register indicate the sign of the result of an operation. Now you have to find out whether the leftmost bit is positive or it is negative. I mean, the leftmost bit is 1 or 0. So look at this example. Suppose the example is move AX 15 and AX 97. Okay, so after this operation, what will be the value of sign flag register? What is sign flag register? This flag register will indicate the sign of the result after an operation. So the binary representation of 15 is, what is the binary representation of 15? This AX is 16-bit register. Okay, we can take AL. Okay, so for AL, we need to write 8-bit number. So it will be 00001111. Okay, and what about 97? 97 is 01100001. So this is the binary representation of 97. If we add 15 with 97, what will be the result? 5 plus 7 equals to 2. With a carry 1, 1 plus 1 equals to 2, 2 plus 9 equals to 112. And look, if these are signed number, that means 15 and 97, these two numbers are positive number. And the result we got 112. It's also a positive number. Now look at the binary representation. If we add these two numbers, the result will be 1 plus 1 equals to 0, 1 plus 1, 0, 0, 0, then 1, 1, 1, 0. The decimal number of 01110000 is 112, right? Now look at your MSB. The MSB is 0. That means the number 112 is actually a positive number. So when the leftmost bit is 0, that means the number is a positive number, and at that time the value of sign flag register will be 0. What is sign flag register? It will indicate the sign of the result of an operation. Now, in this example, we just added two positive numbers. These are signed number, plus 15, plus 97. And after that, we got a result where the MSB is 0. That means the result is also a positive number. So when the result is a positive number, then the value of sign flag register will be 0. But if the result is, if in this result the most significant bit is 1, then sign flag register's value will be 1. Clear?
Yes, ma'am.
Yes.
Okay, now look at this example. Move AL. We can use the same instruction, but this one will be changed. Now the next operation will be subtraction. So sub AL 97. Look, these 15 and 97, these are signed number and their sign is plus. Plus 15 plus 97. So what will be the result of this subtraction? What is the result of this subtraction?
Minus
5 minus 7, that is 2. 1 minus 9, 8. So the result will be minus 82. Right? What is the binary representation of 15? The binary representation is 0, 0, 0, 0, 1, 1, 1, 1. What about 97? 0, 1, 1, 0, 0, 0, 0, 1. But we know that for subtraction operation, we can do one thing. We can at first find out the 2's complement of 97. That means we are going to find out minus 97. Then we'll add it with 15, right?
Yes, ma'am.
Yes.
Look, 15 minus 97 and 15 plus minus 97. These are same thing, isn't it? So now
Yes,
we are going to figure out minus 97. So what will be the 2's complement of 97? This is the binary representation of 97. Plus 97, right? But we need to find out the binary value of minus 97. So we will apply 2's complement method. So after 1's complement, we will get 1, 0, 0, 1, 1, 1, 1, 0. Then add 1. So the 2's complement or minus 97 equals to 1, 0, 0, 1, 1, 1, 1, 1. So we are going to add this value with 0, 0, 0, 0, 1, 1, 1, 1. So minus 97 equals to 1, 0, 0, 1, 1, 1, 1, 1. Now we are going to add these two numbers. So what will be the result? 1 plus 1, 0. Will they carry 1? 1 plus 1, 0. 0 plus 1. 1 with another carry 1. 1 plus 1, 0. 0 plus 1, 1. Will they carry? And 1 plus 1, 0. 0 plus 1, 1. Then 1 plus 1, 0, 1, 0, 1. Now look at the result. 1, 0, 1, 0, 1, 1, 1, 0. Look at your most significant bit. Now the most significant bit is 1. That means the result we got is actually a negative number, right? So at that time, the sign flag register will be 1. Clear?
Yes, ma'am.
After some arithmetic operation on signed number, if the result has a, look at the MSB. If the MSB is 0, then sign flag register equals to 0. Otherwise, sign flag register equals to 1. Clear? Is that clear?
Yes, ma'am.
Okay, so this is sign flag register. Now the next
Ma'am, if
one
there
is,
is overflow,
sorry. Hello.
oh ma'am, I was talking about if there is overflow in there, so we will discard the first number and consider the
Your voice is
MSB,
not
right?
clear. Hello. Hello, Sharif. What is your question?
Okay, ma'am. My question was, ma'am, if there is a overflow situation, then we will discard the first number and
No. Look, why you have to discuss? It's not carry flag, Sharif. When you are going to count the overflow register, at that time you will not get any carry bit. So no bit will be discarded. What is overflow register? After an operation on signed number, if the result is out of the range, then OF equals to 1, right? So look at this instruction. Suppose move AL 115 and AL 80, 180. So what will be the result of this addition? 115 is signed number, so it's a positive number. 180 is also positive number. So what will be the result of this addition? The result will be 5. 1 plus 8, that is 9. 1 plus 1 equals to 2. 295. So what will be the binary representation of 295? Hello.
Yes, ma'am.
What will be the binary value of this?
100.
Okay, 100.
100. 111.
Okay, so how many bits are there?
9 bits.
9 bits. So what will happen to the leftmost bit? What will happen to the leftmost bit is your actually the value of your overflow flag register, isn't it? That value will be stored inside that flag register. Clear?
ma'am, for this result, what will be the sign flag?
Okay, look, the result will be without the leftmost bit because the leftmost bit is the value of your flag register. It will be stored there. And the rest of the 8 bit, that is your result bit. If the result is suppose the result is 1001111010. So how many bits are here? If the register is 8-bit register, there are 9 bits. So this is the value of your overflow register and this is your result. Clear?
Yes.
Is that clear? Okay. Now the next one is auxiliary flag. So now your destination operand can be 8-bit register, it can be 16-bit register, or it can be 32-bit register, right? 8-bit register, that means it can be AL, AH, or 16-bit register, that means it can be AX, BX, CX, DX, or 32-bit register, that is extended EX or extended BX. Okay, so when some arithmetic operation will be done on 8-bit register or 16-bit register or 32-bit register, okay, at that time you just have to find out what is the result of the last 8-bit operands. I'm giving an example. Suppose the example is move AL 43 and AL 94. So these 43 and 94, these are some decimal numbers, and what will be the result of this addition? The result will be 3 plus 4 equals to 7, 4 plus 9 equals to 13, right? So this auxiliary flag indicates whether an operation has produced a result that has generated a carry out or a borrow into the low order 4 bits of 8, 16, or 32-bit operands. What does that mean? At first, write the binary representation of 43. 43 equals to 0, 0, 1, 0, 1, 0, 0, 1. And AL is 8-bit register, so this is a lower byte and this is your higher byte. right? So these 4 are the low order bits and these 4 bits are high order bits. Clear? And what is the binary representation of 94? The binary representation of 94 is 0, 1, 0, 1, 1, 1, 1, 0. So now this 94 is also 8-bit number. So these 4 bits are your low order bits. 1, 1, 1, 0 and low order bits 0, 1, 0, 1 is high order bits. Now add these two numbers. 1 plus 0 equals to 1. Did you get any carry? No, right? Then 1 plus 1, that is 0 with a carry 1. 1 plus 1 equals to 0 with a carry 1. So 1 plus 1 equals to 0. 0 plus 1 equals to 1 with a carry 1. This is your low order bits and this is the high order bits, right? So when the low order 4 bits will produce a result which will be added to the next bit of your high order 4 bits, at that time the value of auxiliary flag register will be 1. I'm repeating it. This is the low order 4 bits and this is high order 4 bits. That means this is your 4th bit. This is the last bit of your lower byte and this is the first bit of the higher byte. So when the lower byte will produce a carry which will be added to the first bit of your higher byte, at that time auxiliary flag register's value will be 1. Otherwise it will be 0. Is that clear?
Yes,
Yes,
ma'am.
ma'am.
Okay, so I can give you another example. Suppose move AL 12, move AL. What is the binary representation of 12? 0, 0, 0, 0, 1, 1, 0, 0, right?
Yes, ma'am.
0, 0, 0, 0, 0, 1, 0, 1. And this is a binary representation of 5. Now add these two numbers. This is your 4 low order bits and this is 4 high order bits. And how the value of auxiliary flag register will be changed? It will be changed when the low order 4 bits will produce a carry bit which will be added to the next position, to the next bit of your high order bits. So now add these two numbers. 0 plus 1 equals to 1, 0 plus 0 equals to 0, 1 plus 1 equals to 0 with a carry 1, 1 plus 1 equals to 0 with a carry 1. So now tell me what will be the result of auxiliary flag register?
1.
Very good. Auxiliary flag register equals to 1. So this is your low order 4 bits when the last bit of your low order byte will produce a carry. That time the auxiliary flag register's value will be 1. So what about this example? Suppose add 7 with 2. Add 7 with 2. That means the instruction is move AL7, add AL2. Seven, that is 0, 0, 0, 0, 0, 1, 1, 1. What about 2? 0, 0, 0, 0, 0, 0, 1, 0. Now what will be the value of auxiliary flag register? 1 plus 0, 1, 1 plus 1, 0, 1 plus 1, 0, 1, then 0, 0, 0, 0. Now what is the value of auxiliary flag register?
0.
Very good, 0. Look at your low order 4 bits. These are your low order 4 bits and we didn't get any carry in this position. That's why auxiliary flag register equals to 0. So when the low order 4 bits will produce a carry, at that time AF equals to 0. So this is for 8-bit register. What about 16-bit register? Suppose the instruction is move AX 120 and AX 95. Now find out the value of auxiliary flag register. Now AX is 16-bit register, and remember that always we will consider the low order 4 bits. Okay, so now write the binary representation of 120 for a 16-bit register. 120D equals to what? What is the binary value of 120? It's 1111000. Is it so? 1111000.
Yes, ma'am.
Yes, ma'am.
So it's a 7-bit number. That means we need to add how many extra bits? 9 extra bits, because AX is 16-bit register. So the binary representation will be 0000000000 111100. What about 95D? 00000000, then 1. So that's 0 1 1 1 1 1. Is it correct? Please check it. 1 0 1 1 1 1 1.
Correct, ma'am.
It's correct. Okay. So now if we add these two numbers, what will happen? This is a 16-bit number. And can you identify the lower 4 bits of this number, of this binary number? The lower 4 bits is 1000. And for the second number 95, this is the lower bit. Now add these two numbers. 0 plus 1 equals to 1. 0 plus 1 1. 0 plus 1 1. 0 plus 1 1. Look, these 4 bits now didn't produce any carry bit. That's why the value of auxiliary flag register will be 0. Clear? Is that clear?
Yes,
Yes,
ma'am.
ma'am.
So this
No,
is
ma'am.
for carry
And
in.
isn't it 1 plus 1 is equal to 0?
Sorry.
The addition, ma'am. Isn't it 1 plus 1 is equal to 0 and carry 1?
0 plus 1 equals to 1. 0 plus 1 equals to 1. 0 plus 1 equals to 1. Okay, this is 1. Sorry. So 1 plus 1 equals to 0. Now there is a carry. Very good. So it will be 1. Okay. I actually missed the sequence. Look, the 4th bit is 1, and in the second number, the 4th bit is also 1. So 1 plus 1 equals to 0. It will create a carry. Very good. So the auxiliary carry flag equals to 1. Clear? So this is for carry into auxiliary flag register. That means when it will produce a carry. But what about borrow? Suppose in this subtraction operation, move L 43 sub L 92. So 43 minus 92 equals to, what will be the result? 43 minus 92. 49, right? 43
Yes, ma'am.
minus
Yes, ma'am.
92 minus
49.
49. Okay. So for this subtraction, what will be the value of auxiliary flag register? The binary representation of 43 is 0, 0, 0, sorry. 0, 0, it will be 1, 0, 1, 0, 1, 1. What about 92? Okay, let's take 94. So at that time, the result will be 4 minus 3 equals to 1. It's 94, then the result will be minus 51. Okay, so what is the binary value of 94?
0 1 0 1 1 1 1 0.
0 1 0 1 1 1 1 0, but we are going to subtract 94 from 43, so we can use the 2's complement here, right? That means we can add minus 94 with 43. So what is the 2's complement of 94? The 2's complement of 94. 1's complement is 1 0 1 0 0 0 0 1, and plus 1, that is 1 plus 1 0 1 0 0 0 1 0 1. So this is minus 94. So we'll add minus 94 with 43. 1 0 1 0 0 0 1 0. So we are not actually subtracting the second number from the first one. So how will we take the borrow? We're going to add minus 94 with 43. At that time also we'll get a carry bit, right? 1 plus 0 equals to 1. 1 plus 1 equals to 0. Then 1. Then 1. Is there any carry bit?
No, ma'am.
No, ma'am.
No. So let's forget about the 2's complement. We'll just subtract 94 from 43. So use the binary subtraction method. So if we subtract, the first number is 43, 0, 0, 1, 0, 1, 0, 1, 1, and 94 equals to 0, 1, 0, 1, 1, 1, 1, 0. Now, how we're going to subtract the second number from the first one? 1 minus 0 equals to 1. 1 minus 1 equals to 0. 0 minus 1, that means we're going to take a borrow from this position. So 1, and in this position the value is 0, 0 or 1. The position of this bit is 0, is 1, 2, 3, right? And from which position we took the borrow? Hello. Did you forget the binary subtraction? To subtract the second number from the first number. And is it 0? Please calculate it. This is the lower 4 bit of the first number, and this is the lower 4 bit of the second number. The third bit is 0, so we can't subtract 1 from 0. That's why we'll take a borrow from this bit, isn't it?
Yes, ma'am.
Yes, ma'am.
And which amount actually we are adding with this bit 0? In decimal, we are actually adding 2, isn't it?
Yes, ma'am.
So 2 minus 1 equals to 1. Then after taking a borrow, now what is the value of this bit? What is the value of
Ma'am,
this bit?
0.
Very good, 0.
0.
0, right? That means in this position, we need to take a borrow. So we are going to take a borrow from the high order 4 bits. That's why the value of auxiliary flag register will be 1. Is that clear? This is your last bit of the low order 4 bits. And when you take a borrow from these high order 4 bits, at that time, the value of auxiliary flag register will be 1, because this is the definition that the auxiliary flag always indicates whether an operation has produced a result that has generated a carry bit or a borrow bit from the low order 4 bits to high order 4 bits. that time the value of auxiliary flag register will be 1. So when a carry bit will be added from the low order 4 bits to high order 4 bits, at that time auxiliary flag register will be set, and when we are going to take a borrow from high order 4 bits, then its value will be 1. Clear? Is that clear?
Yes, ma'am.
Okay. So this is the 5th status flag register. Now the last one
Yes,
is the parity register. Okay. The next one is PF or parity flag register. So do you know what is parity bit? There are two types of parity bit. One is called even parity, another is odd parity. But we are not going to, use that odd parity or even parity method here. Okay. So what is parity flag? Suppose in this operation, you're going to add two numbers, move AL 53, and the second number is add AL 89. Okay, so what is the binary representation of 53? 53 equals to 0, 0, 1, 1, 0, 1, 0, 1. And this AL is 8-bit registered. And 89 equals to 0, 1, 0, 1, 1, 0, 0, 1. Now, if we add these two numbers, what will be the result? 1 plus 1 equals to 0, 1. 1 plus 0 equals to 1. 0 plus 1, 1. 1 plus 1, 0. 1 plus 1, 0. 1 plus 1, 0. 0 plus 1 equals to 1. So this is the result of this addition. Now we have to count how many 1 bits are present in the result. How many 1 bits are here?
4.
The number of parity bit is 4, that is even. So when the result has even number of 1 bit, that time the parity flag register's value will be 1. So how we can define the parity flag register? We can say that this flag register indicates the parity of the 8-bit result produced by an operation. That operation can be addition, subtraction, increment, or decrement. And if this result has even number of 1 bit, then the parity flag register will be set. Clear?
Yes, ma'am.
And if the number of 1 bit is odd, then parity flag register's value will be 0. Okay, so what will happen if the destination operands are 16-bit registered? Suppose now you're going to add 256 and 90. So 256 plus 90 equals to 6, 5 plus 9 equals to 14, 346, right? So each of this number will be represented by how many bits? 16 bits, right? Can you write the binary representation of 256? 256 equals to what?
8, 1, ma'am.
8, 1 bit. No. 8, 1 bit equals to 255.
Ma'am, 1
Then
and
8 zeros,
0.
right? 1, then 8 zeros. So it's 16-bit representation will be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. Right? What about 90? Equals to what?
1,
And
0,
this
1,
is
1,
a binary number. 90 equals to? Hello.
Yes, ma'am.
Yes, ma'am.
Yeah, 90 equals to what? I just want to know the binary value of 90.
10
1011
010
1011
010.
011
010.
010. Okay. So we need to add 9 extra zeros. 0 0 0 0 0 0 0 0 0 and then 1 0 1 1 0 1. I missed a sequence. Sorry. So it will be 0 0 0 0 0 0 0 0 0. After that 1 0 1 1. Again, there is a mismatch. Yeah, there will be 1 extra 0. 1 0 1 1 0 1 0 now. Okay. So after adding this two number, you'll get the result 0 1 0 1 1 0 1 0 1, and there will be 7 0 bit, right? Now look at your result. The result is a 16-bit number, isn't it? This is a 16-bit number, and this is your lower 8-bit. This is a lower 8-bit, and this is your higher 8-bit, right? So in this 16-bit result, how many 1 bits are present? 1, 2, 3, 4, 5. Does that mean parity flag equals to 0? What do you think? This is your 16-bit result, and the lower order 8-bit is 0, 1, 0, 1, 1, 0, 1, 0, and there are total 4 1-bit, and this is your higher 8 bits where the number of 1 bit is 1. So what will be the value of parity flag register? Look, always we have to consider the lower 8-bit. It doesn't matter whether the result is 16-bit number, 32-bit number, always count the number of 1 in the lower 8-bit. So this is our lower 8-bit, and in this 8-bit, the number of 1 bit is 4. That's why parity flag register is set. Okay, so the result can be a 16-bit result, it can be 32-bit result, but we always have to count the number of 1 bit in the lower order 8 bits. So if the number of 1 is even, parity flag equals to 1, otherwise parity flag equals to 0. Is that clear?
Yes, ma'am.
Yes, ma'am.
So please don't make a mistake. This is 16-bit number and there can be some other 1 bit, but we will not count the 1 bit wire in the high orders 8 bits. Always take the low order 8 bits and then count the number of 1. So this is all about
auxiliary flag, ma'am.
what is auxiliary flag.
What is the value of auxiliary flag, ma'am? In that example, 16-bit example.
Okay, very good. Look, this is your low order. In auxiliary flag register, we will take only the low order 4 bits.
But
And
ma'am,
4 bits equals
but
to
ma'am,
1 nibble.
16-bit, ma'am,
And
the lower byte is 8-bit, ma'am.
I'm not talking about lower byte. I'm saying that low order 4 bits.
Oh, okay, ma'am.
In auxiliary flag register, always take low order 4 bits. That is a nibble. 4 bit equals to a nibble. So always take a low order 4 bits. Clear?
Yes, ma'am.
Okay. Thank you.
Ma'am,